Okay. Now, what was that question again? So what did you say? You said number 9. Is that what you said? 11.5. Okay, good. That's a nice place to start today. They gave me 2 points, and they want the parametric equations of the line. Right. So that's good. I like that. So in 11.5, you're asking about number 9. Just to set this up, you know, for a line, what we did was we wrote x, y, and z. We wrote it as parametric equations in terms of t, x naught plus at, y naught plus bt, z naught plus ct. Together, it's a line. I mean, it's a set of parametric equations that describes a line in space. It's a set of parametric equations that describes a line in space. Let's say this again, parametric equations. And now, hang on, before I get to that question, there was something I left out of the discussion the other day because I'm not that interested in it, so I leave it out, but then the book has it, I sort of forget. And what they say there's another version for these lines. They say there's what they call symmetric equations. Watch this. You know, if you solve this for t, I mean, you guys are good algebra students. If you solve for t, I think it would be x minus x naught over a. Do you agree with that? Subtract the x naught, divide, and we just solve for t. Okay? If you solve this one for t, it's y minus y naught over b. And if you solve this one for t, it's z minus z naught over c. And then since that's t and that's t and that's t, then they set these equal to each other. And they kind of, this is another way to describe a line in space. And they call it symmetric equations. I don't know, I don't like them. I do this. I do parametric equations. I don't really like these as much. I can go back and forth if they want me to, but I don't need 2 versions. But if I'm reading the book, and if you're reading the book, you need to understand this for a minute. When it comes to my test, I'll be talking like this, I think. But it's just a different way of describing a line. It's interesting, it's funny, it's set this equal to this equal to this. You know, again, when you see this line, what you're supposed to realize is that it contains the point x naught, y naught, z naught. So I guess that means when you read this, it contains the point x naught, y naught, z naught. The other thing you're supposed to know about a line is that it's parallel to the vector. The line is parallel to the vector ABC. ABC. That was all in 11.5's notes from last class, kind of, but I'm reminding you of it. Anyway, when you read this, I guess you should realize it's parallel to the vector ABC. But anyway, I like to take, when I have this, I take this and write it like this, whatever. Now, his number 9. I think his number 9 gave you 2 points. If it gives you 2 points, we did a problem like this. Find the set of parametric equations, and part B, they want symmetric equations for the line through these 2 points. 5, -3, -2, -2/3, 2/3, 1. Wow. 5, -3, -2, and -2/3, 2/3, 1. Well, if I'm going to write parametric equations, then I'm going to just put one of those points right here. And guess what? It doesn't matter which point it is. I'll just put this point, 5, -3, -2. I mean, that's my point. And then I need this parallel vector, AT, BT, and CT. I need the A, B, and the C. You know, if you got 2 points and you're trying to make a line in space, how do you get yourself a parallel vector?
Multiply by a scalar, or a multiple of
Wait a minute. I'm looking for a line in space. I'm trying to get the equation of a line in space. I got 2 points, and I need a parallel vector, A, B, C. How do I get a parallel vector to my line?
Subtract the second and the first.
Sure. Terminal minus initial. And it doesn't matter who's terminal or who's initial, but you subtract and you create that vector, and boom, that's your A, B, C. Right, that's your parallel vector. Maybe you were trying to say that. Anyway, I need to just subtract and I'll get the vector. You're exactly right. And then I'm subtracting these things that, I need a common denominator. I mean, I need a common denominator. 15/3 minus a negative 2/3 is 17/3. Negative 9/3 minus 2/3 is negative 11/3. I think I did that right. Negative 2 minus 1 is negative 3. I think that's my parallel vector. I think that's my parallel vector, and I subtracted one point from the other. I didn't care which parallel vector I got, that one or the other one. I don't. So terminal and initial don't really matter in this case. I just need a vector. So now I'm ready to write the answer, and I would write 17/3 t and negative 11/3 t and negative 3t. Are you guys okay? So did that kind of answer your question?
The back of the book, the answer is 5 plus 17/3. I mean, not 17/3, it's 17.
Okay, well here's another option. See, because here's the thing. Any parallel vector works. So it doesn't have to be him. Guess what it could be?
Times 3.
Any parallel vector works. So any scalar multiple of him would work. So there's millions of answers, to tell you the truth. And what they might have done to avoid the fractions is they might have multiplied by 3. And they might, instead of dealing with v, they might have dealt with 3v, which looks a little nicer. 17, negative 11, and negative 9. And there you go. So that answers your question. I probably could have answered that without doing the complete problem, but it's a good little problem.
Yeah, that's what they did.
Yeah, that's it. So when we do these, that's one of the things. When we look these answers up, there are more than one correct answer. In other words, they also didn't have to use that point. They could have used that point, as a point. But they also could use any parallel vector. So for convenience, they just multiplied by 3 and use those numbers. Yeah, I got you. That's cool. And this is, anyway, given 2 points, find the equation of a line is a fairly easy little problem. It'll probably show up on next week's test. Gonna have one easy question on next week's test. But cool. And then anyway, we reviewed that thought. This funny thought. Anything else? Any other requests from homework? Here's a funny question. Here, I'm gonna do one here. 14. I'm in 11.5, and this question is a little bit tricky, I think. So again, now here's the question: find the equation of the line, if you don't mind. Find the parametric equation or the equation of the line. So they want me to find the equation of a line. There's kind of a batch of these questions. Find the equation of the line. And 14 says the line passes through the point negative 4, 5, 2. So it goes through a point. That's nice of them. Tell me a point. That's real nice of them. It almost makes me want to start writing the answer, right? I mean, I'm going to put my negative 4, 5, 2 right there. I mean, that's a point, I know, on the line. But then they tell me something else. They say that this line, we're talking about an infinite line in space, this line is parallel to the xy plane and the yz plane. That's kind of interesting. This line is parallel. It's also parallel to the xy plane and the yz plane. So this is a problem. I mean, some problems I just do calculations, I do work, and I get the answer. Some problems I need to draw pictures and see what the hell's going on. And this is one where I need to sort of draw a picture or walk around this room. I mean, hang on. If I'm in this room, where's the xy plane?
The floor.
Oh, that's the floor. Thank you. That's the floor. Where's the yz plane?
The wall.
That wall is the yz plane. You're right. That wall's the xz plane. there's the origin over there, 0, 0, 0. Yeah, you're right. So how can you be a line that is parallel to the floor and parallel to this wall? I mean, I'm a line. Here I am. I'm a line. Short, little, stubby line. I got to be parallel to this wall, so I can't go cutting through the wall. I can't intersect that wall, I guess. So I got to be like this to avoid hitting that wall. Hey, and I can't hit the floor, so I can't slant down into the floor. So I guess I got to be like this to avoid hitting the floor. Look, I'm parallel to the floor and I'm parallel to the wall. So I'm one of these lines in space, infinite line in space. Now, here's the trick. Because to me, to do these problems, you need a point and a parallel vector. And then you fill in the blanks here. So now that you've figured out what this thing looks like, can you come up with a parallel vector? What would be a parallel vector to this?
Y is the only number that changes.
Thank you. Again, I could sort of draw this on the board. I just sort of did it but what we just decided was your line is kind of cruising this way. Parallel to the floor and parallel to that back wall. Can you come up with a vector that's parallel to that? You said something that's accurate.
Y is the only one that changes.
Right, but can you tell me what that vector is then, or can you?
The X and Y values are.
Yeah?
Not yet, I can't.
Yeah, good. It's this vector. Look, I can see it. He said, I mean, there it is. That vector that goes along the y-axis would be parallel to my line. And what would be the name of that vector? 0,
1, 0.
1, 0. Good. And by the way, it didn't have to be 1. Could have been 2, could have been 3, could have been 8, but 1's good. Good. Once we decided it was, I mean, visually I figured out it was this. And then I needed a parallel vector, which would be along the y-axis would be a good one. And that would be 0, 1, 0. Cool. We figured it out. We figured this out. When I write this up, look how it looks. That's my parallel vector. That's my point, and I fill in the blanks. I got the point, -5, -4, 5, 2. And then watch this. I put 0t. You know, 0t. I won't write 0t. And then I put +1t, and then I put another 0t. So here it is. Which, I just want to say, you know, sometimes I do things like, there's different ways to approach some of these problems. And the one way I like to do it is very robotic, like, here's my formula, what do I need? I'm a robot, I need a point, I need a vector, and I do it, you know? I mean, and I think that helps. I think students like to think I need a damn system, you know, like a robot. But the other way to think is kind of more conceptually. I mean, if this line is cruising like this, you know, you kind of said it, Zachary. Well, let me think here a second again. Who's changing is y. You know, it's whatever x it's at, it's stuck on that x. It's not moving in the x direction, and it's not moving in the z direction. So the x and the z are sort of stuck, and the y gets to move. Well, look at my equation. The x and the z are sort of stuck, and the y gets to change with the variable t, with the parameter t. Anyway, that's a different way to think. Y gets to change. Let's put a variable. I mean, let's put the parameter. Anyway. What you'll notice as you do these problems, like this problem, you know, oh, where was all the hard work you did? You know, nowhere. I mean, it was all kind of just conceptual and visual, and I have to know my way around the x, y, z coordinate system. I kind of got to be able to think. I need to have a good picture of that and be able to think about that in my head or on paper or in this room. You know, I gotta be. That's the trick. I mean, I'm really not doing too hard of math sometimes in this chapter, but I am getting used to 3D world and how to think in 3D. Here's another one. 16 in 11.5. There's a 16 here, and this is just another one about a line. But I'm going to remind you something. So we learned about lines in space, and then we learned about these parametric equations. The key is this kind of, and then I taught you this real quick. This is also in the book for lines, but I'm going to get rid of that. The other big thing in 11.5 was this about planes, and planes have a different kind of equation. They don't have a parameter t. Planes have this kind of equation: a times x minus x. Now I had this down the other day. And what we know here then is that, again, one more time, the details here are that this plane contains a point. It contains a point, of course, x naught, y naught, z naught. And this plane is perpendicular or normal to the vector. It's normal to the vector. The plane is normal, or the vector is normal to the plane, or the plane is normal to the vector ABC, which is perpendicular, and the word normal means perpendicular. So again, you know, a point and a vector. This is also a point and a vector, but it's a different scene. You know, this is a line and it's got a parallel vector. This is a plane and it's got a perpendicular vector. You know. Anyway, this 16 is about, I think this question 16 is about lines again, but then it does bring up planes again here. Let's see what it says. It says, the line, they want me to find the equation of a line, so it's really about finding the equation of a line. But what do they say about this line? They say it passes through the point -4, 5, 2. I think I just did that. They gave me a point. They gave me the same point as they did that other problem. They gave me a point, and this time they say that this line is perpendicular to the plane -x plus 2y plus z equals 5. Wow. The line that I'm looking for is perpendicular to the plane -x plus 2y plus z equals 5. Plus 2y plus z equals 5. That's interesting. That's interesting. Well, again, we've barely been in this section 11.5, and we haven't done much work yet, but here's an important thought here. I said this the other day. So if this ABC is a normal vector, well, here it is in the standard form, but I said this the other day. I said once you distribute this, once you distribute that A, B, and C and collect like terms and everything, it turns out that A, B, and C remain the coefficients on the x, y, and z. So the normal vector to a plane is staring right at you when you're looking at the equation of a plane. The normal vector is the coefficients right there. So this plane, so this plane is a plane in space, and it has a normal vector shooting out of it. There it is. I'm calling that a normal vector. I drew a little perpendicular symbol there. And what is it? It's -1, 2, 1. Now wait a minute. That's all true facts. Okay, I just drew an abstract plane with a normal vector sticking out of it. And I know it. I know what that normal vector is. I can read it out of its equation. Now wait a minute. What am I looking for? I'm looking for a line So if I'm looking for a line, that makes me think of my line equation. Oh yeah, look, they gave me a point. I'm going to fill that in. And now for this line, you know, I need this parallel vector. Now hang on. The line is perpendicular to the plane. So it's a line, you guys, though. So it's a line. It comes, maybe it crosses through that plane and comes out the other side like that. But it's perpendicular to the plane. But what do I need to finish this? I need a parallel vector to my line. Any ideas?
-1. 2, 1.
Yes, right? I drew a great picture for you. The normal vector to the plane is going to be parallel to my line because my line is perpendicular to the plane. My line's perpendicular to the plane, so the normal vector that comes out of the plane is going to be parallel to my line. I can use that as my parallel vector. And I'm done. I don't have to put a 1 there. Are you guys okay? I drew a good picture to try to help explain it. The truth is, there wasn't a lot of work on this one either, was there? Just knowledge of, I needed to know what that vector meant and how it related to what I needed, and I'm done. Right. There's a few more line questions about when do they intersect and how do you can tell if they're parallel or there's some more stuff about lines that I won't get to now. I'll get to those next week. But then starting with 35 through 52, I mean, those are some of my favorite questions, and they're all about planes mostly. It's 35 through 52. There's a big batch of stuff about find the equation of the plane, find the equation of the plane. It's asked a lot of different ways. So those are good problems to get to. I like those. And I might do something here before we quit. The other thing I want to point out, toward the end of this section, there is some sketching of planes, which we practiced. You can practice sketching some planes at the end of 11.5. And then there's some problems about the distance between a point and a plane, and the distance between a point and a line. And guess, I didn't assign those problems. There's a big discussion about that, and there's formulas for that, but I don't get into that. So if you're reading the book, that's a part I didn't, that's a part I excluded from 11.5. Distances between points and planes and points and lines and in space. There's some formulas and concepts there, but I skipped that. Yeah?
Can you talk about one of the sphere problems? I think was it 11.4?
Maybe. And was there one in 11.4? Because those spheres were kind of back in 11.2 mostly.
Sorry, I forgot what chapter.
Yeah, that's okay. Which one? Do you have a particular one?
The dot product formula was U dot V over the magnitude squared. I don't have the actual formula down.
The magnitude of U, magnitude of U times magnitude of V.
Yeah, the sphere one, I think that was squared. The denominator was squared.
See, now I'm having trouble, figuring out what exactly you might be asking there. So hang on. There's this formula, and by the way, you might need this today. U dot V over the magnitude of U and the magnitude of V, and that equals the cosine of theta. And that's just a cool little formula that if you have a vector U and you have a vector V, this formula tells you the angle between them. That's not the angle of standard position. It's just the angle between two vectors. But anyway, none of this relates to spheres, I don't think, to me. But anyway, just thought I'd bring it up, and you started to sort of talk about that. I mean, I mean, spheres, I mean, I can talk about spheres. Here's a sphere. X squared plus y squared plus z squared equals 1. A sphere is a surface. I never used vectors a whole lot when I discussed spheres, I don't think. I mean, it was just a surface in space. This is one that's centered at 0, 0, 0, and its radius is 1. You know?
Maybe that was just in the textbook. We didn't do it in class.
Well, that's possible. It's possible we ran into something in the textbook that I glossed over or totally skipped over, because I do that. I mean, right, I hit these topics and there's just some stuff I skip over. So maybe that's what you're talking about, something like that. But since you brought up spheres a second, here's an interesting question. Here's an interesting question. Can you find the equation of the sphere that would circumscribe this box? And I think what I'm making here is a 1 by 1 by 1 box. And what did I just say? I want the equation of a sphere that circumscribes this box. Now, and I guess there's really two good questions. Circumscribe the box. Do you even know what that means? And by the way, this box is a cube. I couldn't use the word cube. But find the equation of the sphere that circumscribes this box. Well, that means the sphere is outside the box, and barely outside the box, meaning I think it touches at these corners. It would touch those corners. I mean, the other cool problem would be inscribed inside the box. Inscribed inside the box means the sphere is in the box, and it's barely inside the box, meaning it's touching the box also. I don't think it would touch at the corners, though, do you? Can you imagine this? It would be touching at the faces, I think, then, wouldn't it? Yeah. But the circumscribed sphere would be touching these corners, and I think I'd like to know its equation. I think first thing you might want to do is, can you tell me the center of it?
0.5, 0.5, 0.5.
I think so. I think the center of the sphere that circumscribes this box would also be the center of the box. And the center of the box would be out 1/2, over 1/2, and up 1/2. That would be the center of the box. And that would be the center of my sphere. So I get some partial credit by doing this. This is a sphere centered at 1/2, 1/2, 1/2. And that's that point. Now, I could blow this picture up, it would be a little bit nicer. So that's that point, 1/2, 1/2, 1/2. That's the center. Now what do I want?
The radius.
I need the radius. Yeah.
Would that be the diameter divided by 2?
Sure.
So square root of 3 over 2?
Ooh, damn, he might be onto something.
I think the radius would be 0.52.
All right, hang on. So there's a lot of ideas. You can do this, there's a lot of good ideas. So one way to get the radius would be from the center out to where the sphere. Now again, I haven't even drawn the sphere, but I'm imagining the sphere barely around this thing, which I said means hitting these corners, I think. I think it's hitting the corners. Is it? Jesus, now it's messy. So I think the radius would be from the center out to one of these corners. Listen, what's the name of that corner right there?
1, 1, 1.
Good, 1, 1, 1. That one, yeah. So good. Now I can calculate that distance from 1/2, 1/2, 1/2 to 1, 1, 1. That would be my radius if I calculated that distance. How do I calculate that distance?
Using the distance formula?
I could use the distance formula. Do I know the distance formula? Do you guys know the distance formula?
Yeah.
It's kind of
X
nice
squared plus
common
y squared
sense.
plus z squared, rather. All
Kind of.
squared.
Subtract them. You got to subtract them and square it. Subtract them and square it. Subtract them and square it. Add them up. Take the square root. So we could do that. I like what he said though earlier. Let's go back to what he said. So we could do that. Get the that would be the radius. You know what he said earlier? He said, why don't you just find the diameter and cut it in half? Well, that's true. But the diameter would be, you know, from one corner to another corner. I'd have to imagine that first of all. And if I go from 0, 0, 0 to 1, 1, 1, that would be a diameter. And what would and that is kind of classic. He already told me that. What is that distance?
Square root of 3.
Square root of 3, right? Because it's 1 squared plus 1 squared plus 1 squared and the square root. So it's the diameter, which is the square root of 3, and then if you divide it by 2, that's your radius. So what goes here? Square root of 3 over 2? Squared. Squared, right? Radius squared, right? If I would have done this distance, I would have got the radius. It should have been square root of 3 over 2. What would it have been? It would have been 1/4 plus 1/4 plus, hang on. It would have been 1/4 plus 1/4 plus 1/4 in a square root. That's the square root of 3/4. Oh, that's the square root of 3 over 2. Damn, that's my radius. Whew. I love math. It works no matter what you do. Anyway, that's it. That's my equation of my sphere. Again, I don't want you foiling it out. You could square that for me. That would be 3/4, I guess. Would be my radius squared, but that's kind of a cool question about a sphere. Yes?
Would it be just as exact, I remember you don't like decimals too much as far as answers, but wouldn't it be just as exact 0.75?
Yes. I can't argue with that. You're right. The answer is 3/4, and you write 0.75. No matter how much I hate decimals, I can't mark you wrong. Damn. Damn math. Damn laws of math won't let me mark you wrong. But if it's 2/3 and you write 0.67, that pisses me off. You've rounded it off. You get to take off full credit.
How many decimals do you have to write for that to be correct?
Forever. Actually, there is a way around that, actually. What is the way around that?
Line bar.
Yeah, you do that little line there. I can't mark you wrong. Damn it. All right. Now you got me again. You got me. Foiled by the decimals. Let's do one more problem before we quit today. We're going to quit and take a quiz. I want to do a plane problem. I just thought there's a lot of these good plane problems. Find the equation of the plane. Find the equation of the plane. Do you know what to do if someone gives you 3 points?
Just do terminal minus initial. Get a vector.
We did this the other day. We did it the other day. You want to do another one of those?
Yeah.
Or no? Yes? Okay.
Yeah.
All right, let's do another one, though. So I'm saying this is the classic guy. There's other good questions, but let's just do this classic one again. If I want the equation of the plane, I say this, find the equation of the plane, or I write it out a little better than that. Find the equation of the plane, and then I say it goes through these 3 points. 4, 5, -2, 8, 1, 7, -10, 0, 3. And we talked about how 3 points do determine a plane. There is a unique answer to this. There is one plane that contains these 3 points. Oh, as long as those 3 points are not collinear, and hopefully I didn't do that by mistake, but I think they're just 3 separate different points. And the idea, again, I'll just help you talk through the thinking, but maybe you've already got this figured out. You know, to do the plane, I want a point. I got 3 points to pick from, no problem. But I want this normal vector. It's got to shoot out, normal, perpendicular to the plane. So our thoughts last week or last class was if I have these 3 points, I can do terminal minus initial, create a vector that's in the plane, do another terminal minus initial, and I don't care which one, but I'll create another vector that's in the plane, Once you have two vectors that sit in the plane, the cross product will give you the normal vector. And then you're ready to fill in the blanks over here, right? So let's just knock that out. I'll race you. No, I'm kidding. That's an 8. I'm going to create a vector by subtracting terminal minus initial. Maybe I'll subtract this way. 8 minus 4, that's a 4. 1 minus 5, that's a negative 4. 7 minus negative 2 is a 9. I'll create another vector by doing another 2 points and do terminal minus initial. I think this time I'll subtract this way. That's 8 minus negative 10. That's 18, I guess. 1 and 4. Are you guys okay?
Yeah.
And now I've created two vectors that are sitting in the plane, and to finish this problem, I need the normal vector. And I get that by doing a cross product. Cross product, I do I, J, K. I'll do the 4, negative 4, 9, the 18, 1, and 4. And I'll try to do this. Cross product. For I, you cross out I's column and you do this little determinant. That's negative 16 minus 9. You got to do it correctly. Negative 16 minus 9, negative 25. Then I cross out J's column and I do 16 minus
162.
162. 16 minus 162 is negative 146. But the J term gets that automatic negative sign, which I think makes it positive 146. Comma. 4 minus a negative 72. That's 4 plus 72. That's 76. Wow, those are some nasty numbers, but who cares? It's my normal vector. And I can take my normal vector and one of my points, and I can go write the equation of the plane. Here it is. It's this standard form. And don't get the things backwards. It's the normal vector, negative 25 times x plus 10. I'm using this point. 146 times y minus 0. And a positive 76 times z minus 3. And that's it. I mean, in a way, you're done. That is the equation of the plane, but I don't want you leaving it like that. I'll tend to take off a point if you leave it like that. Please distribute it, clean it up, and yeah, like this. That's negative 25x minus 250. That's 146y. That's 76z minus 228. And it equals 0. I would gather my numbers together, move them to the other side, and write negative 25x plus 146y plus 76z equals, yeah, on this side it's a negative 478, but when you move it to the other side, it's positive 478, I think.
Yeah. Yep.
Listen, I'm totally happy with that. You know what the book could do? Sometimes they get a habit of, they don't want the leading guy to be negative, so they'll multiply by a negative, which is okay. Positive 25, negative, negative, and negative introduces a lot more negative signs, but maybe they don't want the leading term negative, whatever, it doesn't matter. That's cool, dude. That's the plane that I made up. It goes through these 3 points, and that's the process. There's more good questions in 11.5. You should get up here and work on these plane questions. It makes you think about them. Think about how to come up with this normal vector. There's different ways of coming up with it. Well, we got a half hour left of class. Maybe I should give you your quiz. that I have for you. Maybe you need a little more than a half hour. Maybe you